Okay, so let's continue. This is the third and final lecture in this section on reactive intermediates. And like with all of these lectures, I'm picking out cases where you can't think of conventional electrophile nucleophile, so hence pericyclic reactions, hence carbenes, and hence benzynes. So this time I'm going to look at radicals, where we have single electrons. I should say that when we circulate the material for these lectures, it will include yesterday afternoon's session as well. And this afternoon, after lunch, we will have another tutorial session where I will have some problems based around reactive intermediates, and we'll work through. You can work through them yourselves, and I will come around and talk to you just like I did with the pericyclic reactions case. Okay, so radicals. We're going to look at structure, stereochemistry, chain reactions, that's the main part, and cyclizations, and then finish just to show an example of cascade reactions. So, what about structure? Let's go back. Most radicals can be regarded as being an sp2 hybridized structure, as I've shown here. So 3-coordinate carbon, sp2, with a singly occupied p orbital perpendicular to the plane of the radical. So this is slightly electron deficient compared to normal carbon. So factors which stabilize cations or anions, because this is kind of halfway between a cation and an anion, will also stabilize radicals. Radicals are generally electron deficient, so perhaps a little bit more like a cation than an anion. So the carbon has 7 valence electrons counting towards it, not 8 as in a normal saturated or an anion, and not 6 like in a carbocation. So you can think about radicals being stabilized by inductive effects. So tertiary radicals are more stable than secondary, more stable than primary, the same as for cations. Now I'm calling that inductive effects. You could also think about that as hyperconjugation. There is also some steric relief going from sp3 to sp2, so that is helping to is a contributory factor to the stabilization. Okay, so inductive effects or substituents, the more substituted, the more stable they are, which is the same as you would get with carbocations. And they can also be stabilized by conjugation with pi bonds, just like for cations. So overlap, creating delocalization, which is always creates stabilization, but by having adjacent alkenes in an allylic system, or adjacent arenes, aromatic rings, in benzylic system. That's strongly stabilizing, and I've illustrated that for benzylic radical here, stabilization. You can draw resonance forms which have the unpaired electron in the ortho position or the para position, or obviously the other ortho position. And so you can draw an overall delocalized radical, as in the box there. You can have overlap with unsaturated bonds to heteroatoms. So this is a bit like the stabilization you'll get in an anion. The radical unpaired electron delocalized into withdrawing groups such as nitrile, nitro, sulfonyl, carboxylate, or carboxyl, I suppose, ketones, and so on. That effect is relatively small. It's a 3 to 5 times stabilization. They're electron withdrawing, which destabilize radicals inductively, but stabilize by the delocalization or resonance effect, or M for mesomeric effect, you'll sometimes see that described as. So you can draw this kind of delocalization, spreading of the single electron density over multiply bonded system. So that relates to this. Another kind of stabilization is overlap with lone pairs. So acyl radicals, different ways of writing this. So where you have a single formally an acyl radical is a single electron on the acyl carbon, but you can imagine an electron transfer to give this kind of radical species, or this kind of species where that's actually a triple bond there with a radical or a single electron density in one of the bonds. And this is like if this was a carbocation, this would be like the acylium ions that you can write down for a Friedel-Crafts mechanism, for example. So that's how it relates there. You can do the same sort of stabilization with an alpha aminyl radical. There's a resonance form with an electron transfer, and there's a sort of an attempt to draw that delocalized. So with these, it's arguable where the single electron density actually is, but very often they react through carbon. And here's the nitroxyl radical, similar situation. So an adjacent lone pair atom will stabilize a radical. Now the opposite happens when you have vinyl or phenyl radicals, are very unstable, where unpaired electron is in an sp2 sigma orbital, like this one, or the corresponding vinyl radical. There's no resonance, no overlap. This is a bit like the benzene situation. The sigma bond that's singly occupied is perpendicular or orthogonal to the pi system. So it looks like there should be an overlap, but there's virtually no overlap. Most radical reactions are chain reactions, and they need an initiation step. Commonly used one is initiator is AIBN, azo bis isobutyronitrile, AIBN. If you heat this up to around about the temperature of refluxing benzene, or you shine a light on it, it decomposes in a homolytic fashion to produce these alkyl radicals and nitrogen gas. Oh, I should say here, I suppose, that with these curly arrow mechanisms, in some of the previous, let's go back. No, right. We noticed that. Notice that we're here using these fishhook arrows, in other words, not with a proper arrowhead, but with a half arrowhead. And when you're doing a bond cleavage using fishhook arrows, of course, one electron is staying with each of the two partners of that bond as it splits. So you should really always draw a pair of fishhook arrows, one going one way, one going the other way, when you break a bond to form a radical. Now, we don't always do that. Sometimes we cheat and just draw one of the arrows, and you have to assume the one going the other way. But on this particular slide, I'm drawing both arrows for a bond cleavage. So there we're cleaving this CN bond and this CN bond, one electron from one of those bonds and one from the other one, of course, make the third bond in gaseous nitrogen, very stable, and then we're left with this butyronitrile radical. This butyronitrile radical usually abstracts a hydrogen from something else. I don't know something's gone wrong with the graphics here. There should be tributyl tin hydride in here, butyl 3SNH in here. I have no idea what happened to that. Some problem with the graphics on the computer. To produce the volatile liquid, the isobutyronitrile, and a tributyl tin radical is often what's actually being used in the reaction. So there's just a little bit of AIBN to get the reaction going. There are other ways of getting that starter radical. One of those is to use a peroxide like dibenzoyl or diloroyl, which is just a long chain alkyl group, and that's cleavage of this weak oxygen-oxygen bond, peroxy bond, and of course, as it's a symmetrical bond, then if it cleaves, being weak, it is likely to cleave in a homolytic fashion to produce one electron going each way. So you get two benzoate radicals which decarboxylate and give you phenyl radicals. And then the phenyl radical will then go on and start the reaction off. It might abstract a hydrogen from tributyl, the missing tributyl tin hydride here, for example. A newer method, and you can look up the mechanism how this works, is to use triethyl borane and oxygen, and that gives ethyl radicals as the starter radical. So either this isobutyronitrile radical or the phenyl or an ethyl, or there are other methods. There are relatives of azobis isobutyronitrile which do the same thing, break up to give you nitrogen, and with different groups either side, and so on. The principle is always the same. There's usually a gaseous byproduct, and there will be a radical that goes on and then sets the main reaction going. So these are the initiators. So let's look at the tributyl tin hydride. That's what this is the reaction from the last slide. This bit was missing, I don't know why. So there's the initiation again, focusing on the AIBN. There's this small amount, actually, you don't use much of it, a little bit of AIBN, and tributyl tin hydride, and produces this tributyl tin radical that sets the reaction going. So what does that do? Well, tributyl tin radical usually abstracts an atom from some organic molecule. So X here would normally be a halide, but I'll say a bit more about what else it could be in a moment. So let's say X is a bromide, let's say. So the tin abstracts that, say, bromine atom or whatever it might be, forms the corresponding tin to X, maybe Br, and that gives you an alkyl radical, or a carbon radical in general. Then the carbon radical, depending on what it is, either will react with another organic molecule, which may be the same or different, to produce a new radical, and so it goes on. And it may be, or it may do something, it may cyclize, or it may add to something, and basically you're getting a new radical, and we'll see examples of what's going on here as we look at particular chain reactions. So this bit in the middle here is where the reaction is happening, and then once everything's reacted, then your final radical needs to stop being a radical. So that captures a hydrogen of some more tributyl tin hydride to stop your organic chemistry. then the tributyl tin radical goes around again. So we need a lot of examples, if you like, synthetically useful examples of what's happening on this middle row. It is initiated and propagated to keep the supply of radical going, so it keeps going from here round to here and so on. When does this finish? Well, termination steps that stop the chain. I mean, this main block in the middle will finish once all the organic chemistry is, all the organic molecules are used up. What might stop that chain finishing its work, its synthetic work, is if two radicals meet. That's quite unlikely because the concentration of radicals at any one moment is quite small. So almost everything happens by a radical attacking a neutral molecule and forming a new radical, but not combining with other radicals. But if that does happen, then that's actually not something you want. Two tributyl tin radicals could join up, and that will stop this chain process going on. So things you need to think about when setting up a radical chain process is the relative reaction rates must be correct to favor the desired chain and not the side reactions. And a lot of work is known about that now as to what is feasible and what isn't. So you don't really nowadays have to do the kinetics yourself to work out reaction rates. There's enough in the literature to be able to predict. You add the if it's a tributyl tin hydride, you add that slowly to keep its concentration low so that you never get any of these radical meet radical things. Note that each propagation step involves a neutral species attacking with a radical, generating a new radical to carry on the chain. And that keeps, those numbers 2 and 3 keep the concentration of radical at any time small, so that these radical-radical reactions, which are counterproductive, can usually be pretty much discounted. So what kind of, I mentioned halides, what kind of things can, what kind of other things can be used to start radical chains? Okay, so that's the halide where the tributyl tin radical picks a halogen atom, bromine commonly, off an organic compound to give an alkyl radical, which then does its chemistry. And actually iodides are better than bromides for this, are much better than chlorides. And the organic molecule, the carbon part, can be aromatic, it can be vinyl, it can be alkyl, in other words, almost anything. What other possibilities are there to get radicals started? If you have an alcohol and you make one of these thiocarbonyl derivatives, tributyl tin radical will react with the sulfur here and produce this kind of radical, which then decomposes to give you the alkyl radical. So that's another route to the same carbon radical. You can have abstraction of a selenium group to give a tin selenium compound and a carbon radical. You might think, why selenium, why not sulfur? It will go with sulfur, but it's very slow. I don't really know exactly what the reason is for that. It'll be down to bond strengths, I guess. You can abstract a nitro group from an alkyl nitro compound and get a carbon radical and tributyl tin oxygen, nitroso derivative. The most common, though, is still to do it with a halide and abstraction there. What about the geometry of this kind of process? So it's like an SN2 reaction, except if you look at this, it's not a carbon where the substitution's taking place, it's the halogen where the substitution is taking place. So in that sense, it's a bit different to an SN2 reaction. You can draw the hydrogen abstraction that ends these processes usually as well. So what's going on there? The attack is, it's a sort of linear attack like an SN2 reaction, but it is at the abstracted atom that the attack is taking place rather than at a carbon center. So the sp2 planar radical is attacking a sigma star orbital of say an organic halide or something like that. So that sort of linear attack for the abstraction reaction is the lowest energy pathway based on all the orbitals. Now we have to look at how radicals behave in a polarity sense. If you look at this, if you make this kind of system, which is a stabilized carbocation at this point here, so it's an oxonium ion resonance form, then this center here is an electrophile, and it will react with an electron-rich double bond like an enol derivative. Silyl enol ether here to leave, and the initial product will be a carbocation stabilized by the enol derivative oxygen. If it's a radical at that center rather than effectively a cation, then it behaves in a nucleophilic sense and prefers to react with electron deficient double bonds to produce a radical in the adduct. So it's operating with the opposite polarity to the way that a carbocation would operate at that center. Think about this one in the bottom here, where we have a nucleophilic carbon anion, an enolate, attacking an electron deficient double bond now. So that's a nucleophile attacking an electrophilic center on a double bond, producing an anionic intermediate. If that was a radical there, that's then turns out to be electrophilic and reacts with electron-rich double bonds. These are examples, by the way, these radical processes where I'm drawing the I'm not drawing all the Fischer-Garrows. I could draw another, on the double bond, I could draw another one coming out, sorry, here, I beg your pardon, I could draw another one coming out to meet the single electron coming in. I'm assuming that. So notice here what's happening is that the polarity of the carbon involved, if it was cationic here, is electrophilic. If it's a radical, it behaves nucleophilically. Here, if it's a nucleophile, if that's a radical, it behaves electrophilically. So the polarity is reversed, so it fits into the Umpolung, reversal of polarity family.
But that polarity change due to the second reagent in the last.
Sorry?
In the last section, you have shown the radical as electrophile. So, is it due to the second component?
It's due to the electron withdrawing groups on that radical, making it electron deficient center.
In the upper here, in the second section.
This one?
Yeah, it is shown as nucleophile.
Yeah. Prefers to, well, it does prefer to, I mean, explain, I don't know. The result is this kind of radical prefers to react with electron deficient double bonds. So you have to regard this as nucleophilic. And I suppose you could say that because that's got donation from an adjacent lone pair helping, pushing electrons towards it, whereas here you've got withdrawal by a carbonyl group pulling electrons away. So in terms of the preferred reactivity, these radicals are behaving the opposite way to the corresponding anions or cations. If you have an electrophilic radical wanting to react with an electron-rich EDG, electron donating group, an electron-rich alkene, that produces eventually a radical which is next door to the electron donating group, so becomes a nucleophilic radical. For example, in this case, and if you have a radical that prefers to react with an electron withdrawing, an electron deficient alkene, when that goes through, you end up with an electrophilic radical next to an electron withdrawing group. So you can effectively switch the philicity of the radical by adding it to an appropriate double bond. So I've said they're adding to a double bond. What about the regiochemistry of adding to a double bond? So if a radical, and I've hinted at it in those previous cases, if a radical is adding to a substituted double bond, it will favor adding at the terminal position rather than effectively the branching position. Now that's what I've showed on those previous slides anyway, adding at the terminal position, remote from the substituent on the alkene. So that's favored there. In an intramolecular reaction, we have two choices. Does it add at the near end of the alkene to produce an exo radical, a new radical, or does it add endo to produce a radical in a new ring rather than outside a new ring? And here, generally speaking, kinetically favored is the exo radical, although the endo is thermodynamically favored. But if this is kinetically favored, this will usually be formed, therefore will be formed fastest, and unless the radical can reverse, you'll get the exo cyclization favored. So in a bimolecular reaction, sort of adding at the terminus away from a substituent is favored. In an intramolecular reaction, the addition to the internal carbon is favored to give an exo radical in the product. Kinetically, we'll see that that's only disobeyed if there is any way of going backwards from this to ring opening again and ending up at the thermodynamic sink. But normally you see this exo reaction because it's kinetically favored. And you can see that in cyclizations, a 5-exo dominates over a 6-endo, which would be where this radical acts at the outer end, the remote end of the double bond. So the exo dominates, and the alternative would be 6-endo. And that's kinetically favored because there's no particular driving force for that, no reason for that to reopen. So the kinetically favored product wins there. The same applies in the closure to form a 6-membered ring. So 6-exo dominates over 7-endo. And again, there's no particular reason for this, or driving force for this to reopen. So the kinetic control wins over any thermodynamic preference. Where the thermodynamic preference wins is when you have smaller ring sizes. So if you go down to 4 or 5 membered rings, this time the ring opening is the predominant process, and in fact radicals at this kind of position are used what's called radical clock. And if you have something that will ever produce one of these, if you want to check something's a radical mechanism, you build this kind of cyclopropane unit into your molecule such that if you form this kind of radical, it will come open, and then you'll see products from that. So you can use it as a probe for radicals forming. So 3 and 4 membered rings, the corresponding exo radical goes the other way, it ring opens. So there the thermodynamics win. But if you're forming 5 or 6 membered rings, then the endo closure is disfavored and the exo closure wins. And that's, I say, a kinetic effect. Stereoselectivity. How can we start predicting stereoselectivity of cyclization? This is a model produced by Athol Beckwith in Australia. So the required transition state for 5-exo cyclization, that's 5-exo there. So closure to form a 5-membered ring and produce an exo radical like this. The transition state for that can be imagined to be like a cyclohexane chair, with large groups preferring equatorial positions. So this would be a closure to form a 5-membered ring and heading to the transition state to form a 5-membered ring heading to a 5-exo radical at that position. And you can see this is drawn to look like a chair, only we're closing a 5-membered ring, not the 6-membered ring. But it's drawn, let's say, as part of a chair. And where it's possible, substituents prefer to be equatorial rather than axial. So of course, in each particular case, it depends on the stereochemistry of the precursor that you're cyclizing. But there is this model, the so-called Beckwith model, that you can use to predict stereochemistry, pretending that the transition state is essentially like a chair. If you have a bicyclization to form a double ring, then the observation is that the ring junction you're forming is always a cis ring junction. This is a 5-exo. Again, look, this is closing onto the near end of the double bond and leaving a radical at the far end of the double bond from the initial closure radical. Now, of course, I'm not saying in these cases how the radical was generated and giving the full chain reaction. I'm just showing that if you generate the radical, what can happen to it. And we'll see some examples of real sequences a bit later on. Well, fairly soon, actually, now. Okay, so applications in natural product synthesis. Here's quite an old one from the Stork group in 1985, where he makes uses lithium disopropylamide, strong base, to deprotonate next to this ketone in the bridge here, and then alkylate this primary bromide, primary allylic bromide here. That gives this derivative. If you then treat that with tributyl tin hydride, a little bit of AIBN, and you irradiate it, you shine a light on it to break down the AIBN, the isobutyrylnitrile radicals capture H's off the tributyl tin hydride to make tributyl tin radicals. They abstract a bromine from here to make a radical on this position. That ring closes onto this carbon, the nearest one in the double bond. So that's an exo closure. That produces a radical at this remote position. The radical at that's left over from the double bond you've closed onto takes a hydrogen off another molecule of tributyl tin hydride to produce another molecule which gives the product, which produces the new tin radical, then goes around and takes the bromine off another molecule of the precursor to produce a radical which closes onto the alkene, which produces a radical at the front end of this double bond, which takes another H off the tin hydride, and so on and so on. And that goes on until there's no more of this bromide left. So this is a sort of shorthand way of talking about the cycle. And that's what you end up with. And then that was hydrogenated to give a particular natural product. In fact, the hydrogenation didn't go completely to one face, so that this ratio is just coming from hydrogenation from the two faces of that alkene. But that's illustrating a closure, and it's an exo closure. It's 1, 2, 3, 4, 5, 6. So it's a 6 exo closure in that bridge system. In many respects, that's a relatively simple molecule in natural product terms. Here's another example, again from the 1980s. This is from my old boss when I worked at Nottingham University, Professor Jerry Pattenden. This synthesis is all about setting up this compound. Clearly that's not easy to do. But then you need to cyclize this position here onto this 5-membered ring. An iodide was put in there, and that is the best halide for abstraction, as I mentioned earlier. Bromide's common, but iodide is better. The only snag with iodide is sometimes the iodides are not so stable, so maybe sometimes the bromides are easier to make and keep. But iodides are better for the radical abstraction. So same sort of conditions, not photolysis to break up the AIBN, but refluxing benzene. And what's going on here is that the AIBN breaks up, the radical from that takes up hydrogen from the hydrogen atom from the tributyl tin hydride. Tributyl tin radical takes the iodide from this primary iodide and produces this radical in the square brackets. That radical does its thing now, and that adds to this double bond position. 1, 2, 3, 4, 5, 6. So it's a 6 exo closure. It does it in a stereospecific fashion. It's directed by the chiral centers that are already in the molecule. And that would produce a radical at this position, the bottom position of the double bond. That new radical then takes a hydrogen atom off some more tributyl tin hydride. The new tributyl tin radical takes some more iodide off some of the starting material, and so it goes on until you run out of the corresponding iodide.
But is there any side product when the cyclization would occur under that another double bond?
No, because this one, 1, 2, 3, 4, it would produce that cyclization is a 4 exo, and that's disfavored because of the ring size. But
if you don't another carbon.
Yeah, but 5 endo is disfavored. I know compared to 5 exo, but it's not. 5 endo you don't really see. But there's another factor here, and you've pointed it out, which I was just going to go on to. that this is a double bond with an electron withdrawing group on it. So this is, so the electron withdrawing group lowers the LUMO of this bond, so actually that is more reactive than that double bond anyway, as it turns out. So this one will produce a 4-membered ring or a 5-endo, neither of which is favoured, compared to this, to adding a 6-exo onto a double bond with a withdrawing group on. So it's a fair point, and you're right, you do have to think about the reactivities when you do these. But this has been designed, I mean, you need this carbonyl here in the final product, but it also is designed to assist the radical reaction. I think this bit should be coming down from here. Yeah, forget the it's the radical cyclization I'm focusing on. I think this part is the subsequent transformations from the radical cyclization product. I borrowed this slide from somebody else, so I don't. Yeah, I assumed it was correct, but I never really. Yeah, that's weird. Okay, so this. That should be from there with doing these transformations. But the key here is it's a 6-exo and the nucleophilic radical here is reacting with an electron deficient double bond. In a 6-exo fashion again. Here's another one from Snyder's group. Here's an aromatic iodide. Here's the radical generation conditions. This is not AIBN, but it's a relative of AIBN. And it's got cyclohexyl groups either side rather than the isobutyl groups. There was a period when when you couldn't buy AIBN from suppliers, and people had to use different relatives of it. But anyway, it's the same principle. You've got something that's creating an alkyl radical by decomposition in heating, in boiling benzene again. That's taking the hydrogen off tributyl tin hydride to give the tin radical, and that's doing the abstraction of iodine atom from there to give an aryl radical. And as I said, aryl radicals, like vinyl radicals, are quite reactive, quite unstable, relatively speaking. So that then does a hydrogen abstraction from within the same molecule to give this radical. That radical then adds back to the benzene ring. And here's a slightly different way out for that radical. This one doesn't really want to pick up a hydrogen atom because it would lose the benzene stability. So this radical becomes oxidized. In other words, another electron is taken away from this system. That will give the equivalent of a cation. And I think it's oxidized spontaneously in air in this case. If you imagine an electron going from there, that would give a cation, and then loss of a proton from here would return you to an aromatic system. So there's a slightly different end to this reaction. In the previous cases, the radical formed by ring closure was then taking a hydrogen atom from some more tributyl tin hydride. That's not happening here. This is oxidizing to finish off. And then that builds this complex looking skeleton, which is taken on to this natural product, scolaricine. So aryl radical, is reactive enough to take a hydrogen off somewhere else to form an alkyl radical, and then the ring closure happens, which is again is effectively a 6-exo ring closure onto the benzene ring. And this time, instead of picking up a hydrogen atom to finish the process, there is an overall oxidation taking place. Here's another one from Catherine Parker in the States, who was using radical chemistry to do a synthesis of the morphine alkaloid. So created this ether. And there's the atom we're going to abstract to form a radical. It's an aromatic bromide again, so it's an aryl radical being formed. We said that's reactive, so it looks for one or other of these double bonds to react with. If it reacts with the top double bond, that will form either a 3 or a 4-membered ring, so that's unfavourable. But if it reacts with this one, that's a 5-exo closure to create this radical. That closes now onto 1, 2, 3, 4, 5. I've written that as 6-endo. Oh, yeah, sorry. Okay, so that closes, I beg that is right, so I'm mixing myself up here. This radical now closes onto the other double bond, and it now closes onto the end next to the sulfur. It's a 6-endo this time, and normally that would be disfavored compared to the 5-exo, but in this case, because of the rest of this structure here, for this to cyclize onto the far end of that top double bond is actually just too straight. So this illustrates that those rules about 5-exo, 6-endo, etc. are what will happen if there is a genuine choice. So here, the rest of this sort of cage structure means that it's sterically, geometrically too high in energy for this to go to the left-hand end of the top double bond as drawn and make a 5-exo, which ought to be preferred, but nevertheless it will still go to a 6-endo, which is where this radical comes from. Now here's another different termination step. This does not pick up a hydrogen atom either. This it fragments to lose the thiophenyl radical. Not surprising given the complexity of this structure. This is not the most efficient reaction you've ever seen, but that creates a double bond here by fragmentation to lose the thiophenyl radical. So here's an illustration of where the normal preferences that you expect are overruled by other geometric constraints in the molecule. And then you can see here now how this, once you straighten this out, it looks like this bottom structure, and that gives this alkene, and you can imagine how that might be taken through to morphine. You've made a good part of the basic skeleton there, and this nitrogen side chain is ready to close onto the double bond that came out of the radical cyclization. Now here is a sort of cascade synthesis, or tandem cyclizations you might say, and this is the work of Dennis Curran, who's done a lot of reactions in this sort of field. They wanted to make this kind of skeleton. This is a terpenoid natural product, hirsutine it's called. And its retrosynthesis, looking at that, was to break those two bonds with the wavy lines through them and think, this is what I'll use as my precursor. So this cyclopentene ring here is this cyclopentene in the center there, and we're going to do cyclizations, radical cyclizations, to form the other two 5-membered rings. With quite a lot happening at once here. So the hard work, if you like, comes in assembling this cyclopentene with these appropriate side chains on with the right relative stereochemistry. I'm not going to talk about that. I'm going to talk about what happens when you use the same conditions, tributyl tin hydride, AIBN, warm it up enough for the AIBN to decompose, sort of 80-ish degrees. What happens? Your tributyl tin radical abstracts this bromine atom to give you that alkyl radical. That adds to this double bond here in the cyclopentene in a 5-exo cyclization. Creates a cis ring junction. I said that if you form a bicycle, it's almost always the cis ring junction, and that's a 5-exo cyclization, but what it produces is a radical at the right-hand end, as I've drawn it, of what was the cyclopentene double bond. That's now set up to do a further cyclization onto the remote alkyne that's been built in there. Not cyclization onto an alkene this time, but cyclization onto an alkyne. Again, 5-exo rather than 6-endo. That creates the skeleton that you want at the end. The reason an alkyne was used is because you actually want an alkene in the final product. Creates a vinyl radical, which is very reactive but has nowhere else to go except to abstract a hydrogen from tributyl tin hydride. And that finishes the sequence, and this keeps on going until all of the starting bromide is used up. So I think that's a very nice application of a tandem application of radical chemistry. Some people call it a cascade reaction, because one reaction happens which leads to another one happening. Each case it's 5-exo. It was designed to do that, was designed to keep a double bond in the final product, and in both cases the initial stereochemistry of the substituents on the cyclopentene was designed to get the ring junction stereochemistry you need, because it was known already that these cyclizations almost always give cis ring junctions. So I think that's a very nice illustration there. And with that, I think is the end. Yeah, that's the end of the session. So there, I think I've shown you the general principles of the radical chemistry, some examples, and so what we'll look at in so that's all I've got to do to say about the 3 types of reactive intermediates I've looked at. So what we'll do this afternoon is I've got some problems involving each of these categories, and so we'll work through those, and I guess that begins at 2 o'clock. So that's it for this morning. Thank you.